Hello, friends. Excited to spend a little bit of time with you today. I'm going to go over a problem with you, and I've got it already coded up. So let's go ahead and take a look at it. Get my screen shared here. All right, so here's the question. We want to write a program that prompts a user to enter a number between 0 and 15, and then display its corresponding hex number. There's some sample runs for you. So if you punch in 11, the hex value is B. And if you punch in 5, you're going to get a decimal number of 5. But if you punch in 31, it should say, hey, that's not going to work. So let's go ahead and switch over to Eclipse. I'm using the Eclipse Integrated Development Environment. Any text editor or IDE will work. So here's the question just repeated. I thought before we got started on this, though, it'd be beneficial to talk about why this comes up or where this comes up. So I built this table for you. And the concept here is, in the bad old days, the good old days, we used to do this conversion a lot more frequently. And the concept is, how do you do a mental mapping from a decimal number to a hexadecimal number to a binary number? And so I've seen this pop up working with microcontrollers. I've seen this pop up working with digital logic. I've seen this pop up doing memory address identification, switch configuration, fun stuff like this. It's something that happens. And so you don't have to love this, or it doesn't have to make sense to you, but here's a little bit more of the story. Okay, so when this is a base 10, this is base 16, and this is base 2. And so when you're in these systems, we still have 0. 0 is common to them all. So 0 in decimal, 0 in hex, 0 in binary. Okay, switching over, when we go to 1, again, that's common to them all because everybody has 1, and that's all the same. When we get to 2, things become interesting. Not necessarily for decimal or hexadecimal. They actually stay the same all the way down through 9. Where it gets interesting is binary. Now, what I want you to think back is I want you to think, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, when we do a 10, it's a 1 and a 0. And so the concept behind that is we go from one decimal place to the next decimal place, to the next position over. And what that represents is now 1 times 10 to the 1 plus whatever's behind it. So if we have 12, it's 1 times 10 to the 1, which is 10, plus 2 times 10 to the 0. 10 to the 0 is 1, right? So 2 times 1 is going to be 2, plus 10 gets us 12. And I know that's a long way to think about things, but that long way of thinking about things hopefully is a little familiar to you. And so we'll go through a few more examples as we go along. But how this relates is every position that we switch over in the binary number, we're switching over a power of 2 because it's a base 2 system instead of a base 10 system. So what that means is the number that we see here is 1 times 2 to the 1, which is 2. So that's 2 plus 0. Moving down to line 71, we've got 3. And so let's make sure that this makes sense. We've got 1 times 2 to the 1, which is going to give us 2. And then let's do it on this side. And then we've also got 1 times 2 to the 0. 2 to the 0 is 1. 1 times 1 is 1. 2 plus 1 gives us 3. Okay, moving on. Now we've got 4. So let's check our math on this one. We've got 1 times 2 to the 0, 2 to the 1, 2 to the 2. So 2 to the 2, or 2 squared, is 2 times 2. 2 times 2 is 4, so 1 times 4 gives us 4, plus 0 plus 0. 4 plus 0 plus 0 is 4. Okay, now we'll check the next one. We'll still have this same 1 times 2 to the 2, but now we add to it 1 times 2 to the 0, which is 2 to the 0 is 1. 1 times 1 is 1. 4 plus 1 makes 5. Okay, so we see this pattern continue. Now we've got 1 times 2 to the 2, which is 4, plus 1 times 2 to the first. 2 to the first is 2. So 1 times 2 is going to be 2, and that gives us 6. And we repeat this pattern. Now it's going to be 4 plus 2 plus 1, which is going to be 7. Because this is 1 times 2 to the 2, which gives us 4. 1 times 2 to the 1, which gives us 2. And the last position, 1 times 2 to the 0, which is 1. Okay, so hopefully this pattern is starting to make sense to you, and hopefully this is starting to gel up and go for you a little bit. Now we move to 8. So we had all the ones filled for 7. 1 more than 7 is going to be 8, so that hopefully makes sense. The pattern's starting to fit in. Notice how it's in the 1, 2, 3, 4 position. 4 minus 1 is 3, and that's important because it will count 0, 1, 2, 3. So what is 2 to the 3? Well, that's 2 times 2 times 2. So 2 to the 3 is going to be 2 times 2, which is 4, times 2 is going to be 8. So we're going to have 1 times 8 plus 0 plus 0 plus 0. 1 times 8 is 8. 8 plus 0 is 8, plus 0 is 8, plus 0 is 8. So 1, 0, 0, 0 is 8. And if we just add 1 more to that, it's going to be 9. So that's 1 times 8 plus 1 times 1 gives us 9. This is 1 times now let's look at 10. We've got 1 times 8 plus 1 times 2 to get 10. To get 11, it's going to be 1 times 8 plus 1 times 2 plus 1 times 1. And that's going to be 11. Now, something interesting has happened over here in the last couple of numbers. Let's talk about that right quick. So the general bit pattern is this binary bit pattern. That's the underlying, hey, this is what we want to keep track of. And so network addresses and stuff like that, this range of 0 to 15, this was something that we wanted to be able to address as a single character. And so they came up with the sexadecimal, but I think it was the HP guys or IBM guys, I'm not sure what. Anyway, the folks back in the day didn't want to write sexadecimal, which would have been more in line with the Greek or the Latin or something like that. It's a fun story. I should look it up sometime. But anyway, hexadecimal is what they thought would be more appropriate to write in their technical manuals. And so they recognized this nice little pattern. It goes from 4 zeros up to 4 ones, and they wanted to have this covered. And so what they came up with was the hexadecimal. And so how this works, it goes 0 through 9, and then before it kicks over, it goes A, B, C, D, E, F. And so F represents 15. And so we can see that on our table here. A represents 10, and so this A, B, C, D, E, F lets us get all the full range of this. Okay, and then just for an example, if we're going to have 16, that's going to be represented by, do one more entry in our table, 1, 0, right? And so in binary, this is going to be, that won't work. So that's 16 in decimal, which is, that lines up okay. Okay, 16 in decimal is going to be 10 in hexadecimal, which is going to be 1 times 16 plus 0 plus 0 plus 0 plus 0, which is 16. So anyway, this is a table that kind of walks you through where that goes. And like I said, there's a few interesting applications that you might come across later in life. If not, this is a piece of just interesting trivia or computer science history for you to go and look into. There's some fun stories. But this is kind of what this table kind of helps understand how these things came to be. Okay, so let's go look at the code and let's see what the code looks like. So what I did was I said, I just did a next int, right? Because it can read in lots of good things. So I said, if 10 is greater than the user input. And there, again, the reason why I like to do my if statements this way, if you do a assignment, it'll be like, hey, you can't assign your variable user input to integer. That's illegal. So I don't have to worry as much about what I screw up there. So like we saw on the table, if it's less than 10, it's not an issue because you punch in whatever you were supposed to be. Now, if I was being careful, probably I would do something like this. I would say if 0 is greater than user input, then I would say something like this. Do I already have that line typed? Yeah, let's just grab this line right here, right? And then I would say else if, right? And let's poke that just a little bit right quick, see if I've messed anything up here. Let's test this. So let's do -2, invalid input. Cool. All right. So let's test this right quick with another one. I want to try to get one of these. So let's try 7. So I'm going to punch in 7. That should give me 7. Cool. That is as expected. Okay, now this is not very fancy here. It says the hex value is A if it's 10, and this basically follows off of our table. Just to clean this up just a little bit, the wrap for the break doesn't make much sense to have it down below, so I'm just going to bring that up. Now, Java will tell you that it really doesn't care how these are all organized, as long as you have something that that makes this work. So this is one line of code. This is a separate line of code. We can have both lines on one line as long as we separate them semicolons. So this is just to make it look pretty. So 10, 11, 12, 13, 14, 15, A, B, C, D, E, and F, and we have the default here. And then this last little line of code just says, hey, we opened up this scanner up here. Let's go ahead and close it. All right, so friends, hopefully that little block of code makes sense, and hopefully nothing here seems too out of whack. This is just one way that you can combine a switch statement with a if-else statement. It's a lot of fun. The decimal, hexadecimal, binary numbers is also kind of fun. So there's other ones out there. There's octal, so I'll spare you that one on the table, but octal is another one that was kind of popular for a little while when we used to have a lot less memory to work with. So anyway, I'm going to go ahead and stop my share there. Thank you all for spending a little bit of time with me. I hope you have a wonderful day, and I look forward to working with you later. Take care. Bye.